We're continuing on here, chapter 3, I believe. And we got into bonding last time, and we talked about a couple different types of bonding. We talked about ionic bonding. And remember, when you have an ionic bond, it is always between a metal and a non-metal. And remember that because of those periodic trends that we talked about in the previous chapter, remember metals essentially have all the trends that make them pretty much want to give away their electrons. And non-metals have all the trends of they would like to keep their electrons and actually gain more electrons. So whenever we get these two guys together here, we're always going to get a transfer of electrons in that case. And that's going to result in a cation formation from the metal, an anion formation there from the non-metal. And once again, remember, in an ionic bond, there is no sharing of electrons. It is just simply the electrostatic attraction, the opposite attraction there. No sharing happening in this case of electrons. We could show this like we talked about, for example, with sodium, which is group 1, has 1 valence electron. Remember that the group number on the periodic table will tell you the number of valence electrons something has. And our friend chlorine, which is group 7 on the periodic table, has 7 valence electrons. Again, in terms of the electron configuration, 1s2, 2s2, 2p6, 3s1 for our sodium. Chlorine being 17, 1s2, 2s2, 2p6, 3s2, and 3p5, I think that should be. And again, these are the 7 valence electrons there for chlorine. That is the 1 valence electron there for sodium. So what's going to happen, as we talked about, is it's going to transfer over to chlorine. At that point, sodium will lose an electron, become positively charged. That chlorine there will basically accept that electron, become negatively charged. And once again, that's an ionic bond sort of formation using Lewis dot symbols. We do include the charges here, and sometimes we put brackets around both of them, or at least one of them. And that indicates that there's no sharing of electrons. Again, it's that sort of opposite attraction that holds it. Ultimately, as we talked about, the whole basis of sort of bonding and kind of really the reason of bonding is what happens when sodium loses this valence electron. It is left with a configuration of 1s2, 2s2, 2p6. That is the same electron configuration as neon, which gives it its noble gas configuration by giving away its electron. The chlorine has room for that electron. It's picking up right there in the p subshell, so it picks it up. A little 1s2, 2s2, 2p6, 3s2, 3p6 action. That is the same as 18 electrons are argon's configuration. So remember, really the goal of bonding in a sense is for everybody to end up with the same electron configuration, sometimes referred to as being isoelectronic with the noble gases. As we know, the noble gases are really a stable bunch, and everybody, again, is trying to be like them. As we talked about last time, a reminder again that they are not changing into the noble gas because the protons are not changing, just the electrons here, so they have a more stable electron arrangement than they did. That's what they're kind of looking for. Now, the other type of bonding that we talked about was covalent bonding. And covalent bonding is between two nonmetals. And because it's between two nonmetals, they are located in the same side of the periodic table. Go right or left, one of those. Or just put it right here. It's good. Everyone gets it. Because all the nonmetals are up there, really sort of gathered together. They have very similar periodic trends, and they both pretty much will like to hang on to their electrons. They both pretty much would like to gain electrons. Neither one of them wants to kind of give away the electrons. So what happens, as we talked about with a covalent bond, because they both have similar periodic trends, the best that they can do is sharing of electrons. So we're definitely going to get sharing of electrons happening here with our covalent bond. Now, as we will talk about, the sharing may be equal, or it may be unequal sharing. And if you remember, we talked about sort of those type of names. If we have sort of equal sharing of electrons between two atoms within a bond, you could think of it as almost like a neutral bond, and that is what is known as a nonpolar covalent bond, or just referred to usually as just a nonpolar bond. If we have unequal sharing of electrons, that is what is known as a polar bond or a polar covalent bond. And remember, I think we looked at HF there, and when we look at HF, because of the difference in electronegativity between fluorine and hydrogen, fluorine being more electronegative, again, electronegativity, the ability of an atom to bring electrons towards itself, the electrons in this case will be hanging out a lot more near the fluorine in that bond than it will in the hydrogen. The result of that is it will create a partially negative charge on the fluorine and a partially positive charge on the hydrogen. We also can use what is sometimes referred to as a dipole arrow to indicate that. The arrow always points to the more electronegative side, more negative side, if you will, of the bond, and the back side that makes like a plus sign in it also points or is at the side that's more positive in it. And as we talked about last time, they are partially positive, partially negative charges because there is still some aspect of sharing. So unlike in an ionic bond where the electrons completely jump, here, I think we used the tug of war example with the rope, the hydrogen is still barely hanging on, but he's still holding on to the rope. He hasn't let go yet and let it completely transfer. The one thing that really helps us determine, how the electrons are going to be shared is electronegativity. And we oftentimes will look at the difference or the change in electronegativity. And Pauling came up with a scale of 0 to 4, as we saw at the very end last time. 4 is the most electronegative, and again, not so much on this side. And basically, you just take the two elements that are involved in the bond, you subtract their electronegativity differences. You can take the larger number minus the smaller number, so you get a positive number always. And if you end up with a change in electronegativity that's anywhere from 0 to 0.4, that is usually considered a nonpolar bond. And the nonpolar covalent bond, basically equal sharing of electrons. If you have a difference between above 0.4, which would be probably like 0.3, 0.5, I mean, to below 2, that is some type of polar bond, which means they are not going to share the electrons equally. You're going to have one side of that bond that's more negative and one side that is more positive. And again, that's different than in a nonpolar bond where equal sharing of electrons, basically no side's more positive or the other. Kind of, again, you can think of it like almost like a neutral sort of bond. If you're typically above 2, and it's not perfect in every example, it's usually ionic. And as we talked about last time, essentially, you don't really even have to worry about this one because, frankly, if you see a metal and a non-metal, it's going to be ionic. So you don't really need electronegativity values technically for that. But you can use it for our covalent bonding to decide if it's going to be shared equally or unequally. If you have a difference in electronegativity of 0, it's considered a pure covalent bond, which is still a nonpolar bond, but that's sort of like your perfect equal sharing of electrons in that situation. There's obviously degrees of equal sharing, all the way up to 0.4 is considered still equal sharing. But in reality, it's not perfectly equal sharing here. It is kind of going in one way or the other a little bit, but not enough to be considered a polar bond in this case. Yeah. Any questions on the stuff we talked about last time there? Okay. So I think maybe. So this again is a table of electronegativity values, and it would be provided for you if you needed it. And let's take a look at the three sort of examples that we came across last time. We had something. What did we have there? We had, we'll do sodium chloride. So we had sodium chloride. We had, and we'll do F2 actually. We had F2. And we had HF, right? There we go. That would do that. So again, if we wanted to use these values here to help us determine is it a polar bond, nonpolar bond, or ionic bond, come back. There we go. We could do that. So again, if we go to sodium, we can look on the table there. Sodium is 0.9 right there where sodium's laying up. So we got 0.9 for sodium. For chlorine there, we got 3, it looks like. So to calculate the change in electronegativity, again, it's just simply subtracting. So 3 minus 0.9 going to give us 2.1. Technically speaking, again, that is above 2, and we expect it to be ionic. Once again, you really don't need the numbers because hopefully you can recognize sodium's a metal, chlorine's a non-metal, and it should be ionic. If we come over here to F2, fluorine is 4, and the other fluorine is 4. So if we do the change in electronegativity, we got basically 4 minus 4, which is 0. That definitely falls between the 0 and 0.4. And in fact, this would be considered a pure covalent bond as it has a difference in electronegativity basically of 0. And this would obviously this guy is ionic, and this guy would be nonpolar. And again, what we are talking about here, just to be clear, is the bond. Yeah, so we're not necessarily talking about the molecule as a whole or anything like that, but we are talking about when we do the difference in electronegativity, 9 times out of 10, we're talking about just the bond. There are places where it is both the bond and the molecular polarity. So if we look at hydrogen here, that is 2.1. And fluorine is 4. So if we do difference in electronegativity, that is 4 minus 2.1. That is 1.9. Yeah, that's a pretty big one there. That's going to make this, again, a polar bond, as we know. And if we drew that bond dipole arrow, it should be, again, pointing towards the fluorine here, which is more electronegative in this case. Obviously, if it's a nonpolar bond, you don't have a dipole arrow because there's equal sharing of electrons. Question on that one there. So why don't you try, probably this one's easier to see, I think. Yeah. So why don't you use the difference in electronegativity values here to determine, is it ionic, is it polar, or is it non-polar type bond? If we have a bond between the following things, let's do carbon and hydrogen. Let's do, I don't know, let's do nitrogen and oxygen. Let's do oxygen and sulfur. Let's do nitrogen and chlorine. Let's do cesium and chlorine. Yeah. All right, so for each of those, use the difference in electronegativity to determine ionic, polar, or non-polar here. All right, let's take a look. So again, I'm just gonna look up the values here on the table. We'll start with the carbon hydrogen here. So carbon 2.5, hydrogen's 2.1. So difference in electronegativity, 2.5 minus 2.1, that's a 0.4. That 0.4 is the limit there of nonpolarness, and this would be considered a nonpolar bond. The reason it goes up to that is carbons and hydrogens are pretty much the basis of organic molecules, and they're nonpolar, so to 0.4 we go with that. Again, basically equal sharing of electrons based on electronegativity. We take a look at the nitrogen-oxygen bond. Nitrogen there is 3, and oxygen is 3.5. So 3 and 3.5 can give us a difference in electronegativity of 3.5 minus 3. That is 0.5. That is above 0.4, but below 2, which means this is going to be a polar bond. It means we could draw our bond dipole arrow. It would be pointing in this case towards the oxygen, which has a higher electronegativity. That also means in this bond here, the oxygen would have a partially negative charge. Nitrogen, more partial positive charge as due to the unequal sharing of electrons. Any questions on that one there? Looking at sulfur and oxygen, or oxygen and sulfur. Oxygen here is 3.5 and sulfur is 2.5. So 3.5, 2.5. So once again here, difference in electronegativity, 3.5 minus 2.5. And that is going to give us 1 as our difference. That definitely is above 0.4. And that makes this a polar bond. Once again, here it is the oxygen actually that is more electronegative. So if we were to draw that arrow, it should point towards the oxygen. The oxygen here would be more negative, and the sulfur would be more positive within this bond, again, due to that unequal sharing of electrons. Question on that there. So we'll do cesium and chlorine. So we got some stuff here on opposite sides. So 0.7 looks like, and chlorine there is 3. So change in electronegativity on this particular one is 3 minus 0.7. And that's going to give us, what we got there, 2.3 perhaps. 2.3, which again is above 2. And it is going to be ionic. And again, we really don't need it because it is a metal and a non-metal. So we should know that it is ionic. The last one we have is nitrogen and chlorine. So when I look at nitrogen there, it is 3. And when I look at chlorine, that looks like 3 as well. So that's going to give me a difference in electronegativity of 3 minus 3, which I believe is 0. So that is going to be a nonpolar bond in this case. It's actually a pure covalent bond as well. First off, any questions on how to use the electronegativity values? Now, this also illustrates a really good point, the last one here, that definitely it is possible that you could have 2 different elements that actually have the same electronegativity and will create a nonpolar bond because of that. And that is what is sometimes referred to as the diagonal relationship there on the periodic table. We did nitrogen, right? Nitrogen is further up, but chlorine is further to the right, even though it's down a little bit. So they sort of cancel out their differences and end up with the same electronegativity values. There's a few places that happens. Also, carbon and sulfur does that, and a few other places, as you can kind of see from the numbers there. There is a few places where if their arrangement on the periodic table is diagonal of each other, not directly diagonal, but kind of diagonal 1 over, they will sort of cancel out their differences and can have the same electronegativity value. So you just got to kind of watch out for those. Now, do you need the numbers all the time? The answer is no, you really don't. You can use, in a lot of cases, the general trend in electronegativity and basically make a fairly good guess as to whether or not you'll have a polar bond, really. And one way you can know for sure is, for example, if I had my, we did nitrogen and oxygen here. My nitrogen and oxygen are actually in the same period on the periodic table, and they're the same row. And oxygen is further to the right. So because they're in the same row, oxygen is further to the right. I know oxygen should be more electronegative than nitrogen, and that's probably going to lead me to a polar bond. So even without the numbers, I could pretty much make a good guess. I also would draw my arrow, obviously pointing towards the oxygen like we did above. Same thing if you had something, say, like we looked at oxygen and sulfur. Oxygen and sulfur are actually in the same group on the periodic table. And when you look in a group on the periodic table, electronegativity increases as you go up the group. And we see here oxygen is further up the group than sulfur, and they're both in the exact same group. Again, you really would not need the numbers here to make the guess that it is a polar bond. There should be a difference in electronegativity enough probably to make a polar bond, with oxygen obviously being more electronegative than sulfur and becoming more partially negative. So in a lot of cases, especially if you're comparing things in the same row or the same group on the periodic table in terms of electronegativity, you can pretty much guess if it's going to be polar bond if they are in the same row and they're different spots, or in the same group, obviously, and they're different spots as well. Any questions on that there? All right. So as we've been talking about, again, sort of our breakdown of nonpolar, polar, and ionic. Some people use percent ionic character, not tremendously a lot these days, but it's just another way of referring to polarity. You could probably imagine if you are 100% ionic, you're an ionic bond, yeah. And if you're more on the zero end of a percent ionic there, you are more of a nonpolar covalent bond. And obviously, if you're in the middle there, you're probably more of a polar type bond. So some people will use percent ionic character rather than difference in electronegativity, but it basically will tell you kind of the same thing. So as we saw there, atoms with really widely different electronegativity, especially when we get some of our metals and our nonmetals together. And speaking of that, just a reminder that, that rule of 2 or more for ionic is a general rule. There is definitely some combinations that you could put together that will be, kind of less than 2. For example, I don't know if you did like 2.8 and 0.9 or something like that. If you subtract it, I think that gets you less than 2, right? So there are a few places where you can put a metal and a non-metal together and get enough difference in electronegativity less than 2. So that's why I said earlier, you really don't even need the values. As long as you see it's a metal and a non-metal, it's going to be ionic. And there are some exceptions, obviously, for the ionic greater than 2 being ionic difference in electronegativity. Atoms with similar electronegativity will definitely form more covalent bonds. Again, because of what we've been talking about, they both essentially want to bring the electrons towards themselves. So the best they could do is share. And it is a game of like tug of war with the rope. And the guy that has the more electronegativity is going to pull harder on the rope than the other guy. And it's going to bring everybody kind of closer to themselves. So in general, that is why we know metals and nonmetals typically make our ionic bonds, and we can get a transfer of electrons, while our covalent bonds here is going to end up being more non-metal interaction. All right. So again, as I mentioned, general sort of cutoff for the ionic bond, but the other ones are good cutoffs there to know. All right. So we talked about earlier last time drawing Lewis dot symbols for ionic bonding. We're now going to talk about the steps to follow to draw Lewis structures for covalently bonded structures. And if you follow these steps, you should really end up with a fairly good structure. If you don't follow these steps, you might not end up with a good structure. You might end up with too many bonds, not enough electrons, and those type of things. So the first thing you really want to think about is when you have a formula and you need to draw sort of the Lewis structure for it, you want to think about the logical arrangement of how those atoms are put together. Now, in a lot of cases, it's fairly straightforward, the ones we deal with. We don't get super complicated ones or anything usually in here. But for example, if you have one element and like 3 of another element, usually the one's in the middle and everybody else is attached, to the single element there. But in general, the least electronegative atom should be in the center. So the one that is the least electronegative atom should occupy the center position. Hydrogen and fluorine should never be in the center position. They should really be on the end position for 2 reasons that we know. Hydrogen should only have, again, 2 electrons, right? The duet rule there to get to helium, which means, again, if you put him in the middle, he's going to have a lot more than 2 electrons. The other one is fluorine. Fluorine is the most electronegative element you could have, which means it should not be in the center of your picture. Once you have sort of the logical arrangement, and if by some chance I give you something that I don't think you would know, I would probably maybe tell you how it's put together. Probably the most important thing here is actually counting the total number of valence electrons. And you need to count up the total number of valence electrons in the entire molecule or ion that you are drawing. That number is really important because when you draw your picture, you pretty much need to hit that number right on the nose. You can't have any more electrons, you can't have any less electrons. Your picture has to have exactly that number of electrons. Now, you may be drawing some ions along the way, and as we talked about with ions, if something is negatively charged, which is an anion, it has gained electrons, which means you need to add those electrons into your total when you're counting up the total valence electrons. Otherwise, you're going to be short electrons. And if something has a positive charge, you will have a cation, and we would subtract the, not negative, but maybe positive charge there would be good. We would subtract the positive charge there from our total. Otherwise, you're going to have too many electrons, right? So if you do have something that does have a charge, you got to take that into account to your total number of electrons. Once you have the logical arrangement of what everything should be in terms of their arrangement and how they should come together, and you have the total number of electrons, the first thing you really want to do is make one single bond. Personally, you know, you got like something like this, right? All right, just kind of some arrangement. Gonna make one single bond, which I usually use lines for the bonding electrons. Again, if you want to use dots, you can, but most people will kind of use lines for the bonding. And you want to go from the center atom to all the outside atoms, once again, with a single bond. You should not jump right off there with the double bonds and triple bonds right out of the box. You probably end up with a bad structure and not the right structure. So you really want to just kind of single bond everybody first. And once you do that, obviously each of the lines, right, represents 2 electrons, right? A pair of electrons. So in this case, for example, I have used up 6 electrons for my total, whatever my total might have been in this imagination. All the leftover electrons at this point will go on the outside atoms first in pairs of electrons. So not single electrons, but pairs of electron until all the outside atoms have 8 electrons, right? Our octet rule, except if obviously our outside atom is hydrogen, no dots around it, right? So we would come around here and just fill these up until we basically complete the octet. And at this point, once we fill up all the outside atoms, if we still have electrons that we need to put on there from our total, they then go to the center atom also in pairs. And at that point, you should hopefully be out of electrons once you hit the center part. You may even be out of electrons before you get to the center, but definitely by the time you get to the center, you should be out of electrons. At that point, what you want to do is make sure that everybody has met the octet rule. In my picture up there, everybody has met the octet rule, right? Everybody's got 8 electrons around it. Doesn't matter if they're dots, doesn't matter if they're lines. It's got 8 electrons. Now, if by some chance you get to a situation and you go, well, I'm out of electrons at this point, right? And I have used up all of my electrons at this point, and somebody has not met the octet rule, that is when you should try to fix that by making a double bond first. And you want to sort of exhaust all your double bond possibilities. And if by some chance the double bond doesn't fix it, then you should try to fix it by using a triple bond. So again, we do not want to kind of double bond or triple bond out of the box. We want to kind of save that for a situation where somebody has not met the octet rule. So here we would probably have to do some double bonding to fix this. All right, so let's take a look at a real one here and see, I suppose. So let's say we want to draw nitrogen trifluoride, which is NF3. Again, the first thing I'm going to do is just count up the number of valence electrons in the entire molecule here. Nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which gives me 7 times 3. So we got 21, 26 valence electrons there. So I'm just going to grab the calculator. So this number, again, is really important because I got to have exactly 26 when we're all said and done. Now, logical arrangement here, obviously, I got 1 nitrogen, 3 fluorines. Nitrogen's in the middle. Fluorine is on the outside. It does not matter if you want to put the fluorine up above the nitrogen or below the nitrogen. It's the same thing. Once again, none of those fluorines should be in the middle because it is the most electronegative here, right? So between nitrogen and fluorine, nitrogen is the least electronegative. I'm now going to make one single bond from the center atom to each of the outside atoms. That is 6 electrons, they say. I'm going to try my math one more time here. That's going to give me 20 more electrons left to go at this point, right? So those 20 electrons are going to fill up the outside one, again, as pairs of electron dots. So 2, 4, 6, that's filled. 8, 10, 12, that is filled. 14, 16, 18, that is filled. I have now put another 18 electrons up there. I still got 2 electrons to go. I'm out of room on the outside. So now again, I move to the center atom. I lay me up a couple of electrons there. And now I have put on all 26 electrons. Again, the last thing that we want to check is to make sure everybody has met the octet rule. So we got 2, 4, 6, 8. All the fluorines are the same, 2, 4, 6, 8, 2, 4, 6, 8. And when we look at the nitrogen, 2, 4, 6, and 8 electrons. So everybody has a total of 8 electrons. Everybody has met the octet rule. And we have a grand total of 26 electrons pictured in that drawing. Any question on those steps? So you definitely want to follow those steps. You do not want to do it, I don't know, I call it like piecework. Like people go, well, nitrogen's got like 5, fluorine's got like 7 there, and try to figure out where everybody goes. And covalent bonding, you really probably shouldn't do that because I see in most cases people end up with not the right number of electrons, wrong number of bonds, and all those type of things. You should think of the electrons in this situation as not necessarily belonging to anybody, but we want to kind of as evenly distribute those electrons to everybody that's involved in the bonds as we can, rather than like nitrogen has 5, so I gotta get them like, 3 extra ones there and that type of stuff. So it's better not to try to do it in pieces, because usually that ends up with really bad pictures and not great structures. And just think of it, okay, these are a total number of electrons. I want to kind of evenly distribute it the best that I can to everybody. Any questions on that there? All right, why don't you do our friend, I don't know, do something. Yeah, why don't you do, that's good. Yeah. Why don't you do carbonate? That sounds good. CO3. So once again, we're going to take the same steps. We're going to count up our valence electrons. So carbon is group 4, I believe. There are 3 oxygens. Those are group 6, which is like 7, but next door. -2 is, mean that it gained 2 electrons, right? So we do need to add that to our total, right? So again, if we had a positive charge, we would subtract that from our total. So that's like 18, 22, 24 valence electrons, again, is our total here. When we look at the periodic table, if you can see through the sun there, you got carbon, and then to the right of carbon, you have oxygen. And that means carbon is the least electronegative, so it should be in the center. In addition, there's only 1 carbon and 3 oxygens, so that's probably going to be your one in the center anyways. Going to put carbon in the center. Going to throw some oxygens around here. Going to do a single bond to each of them. Once again, each one represents 2 electrons, so that's 2, 4, 6 electrons. 18 perhaps. There we go. I think maybe not. That seems 4. Yeah. So we got 18 electrons go. So we can go on the outside in pairs. 2, 4, 6, 8, 10, 12, 14, 16, and 18. So at this point, we have used up all of our allotted electrons. And now, again, we do want to make sure that we are good in terms of octet rule. Is everybody good here? The answer is no. The carbon is not so good, right? We have 8 here, right? 2, 4, 6, 8. All the oxygens are identical, so they all have the same 8. Carbon, though, only has 2, 4, and 6, so it is a little short. Doesn't sound like the octet rule there, so that is a problem. So we do need to fix it at this point. Can I fix it by, just dropping myself a couple of electrons there? Is that okay? That is not okay, because now I will have 26 electrons, which is too many. So you can't just put in some extra electrons, although it may make the picture look nicer. So we do need to, in this case, try to fix it. And again, at this point, we're going to try to fix it by making a double bond. And In this case, every single oxygen there are equivalent, so you can make the double bond at any oxygen. Can I just lay myself up a double bond there? I cannot for the same reason, because now I have 26 electrons. My oxygen now has 2, 4, 6, 8, 10 up there on top, which also doesn't sound like the octet rule. It sounds like some problematic situation. So when we actually do make a double bond, what we're actually doing is we're going to take a pair of electrons and we're going to move them in. These are sometimes referred to as delocalized electrons, meaning they can just move around for fun. So we're going to take a pair of electrons and we're going to bring it in to make that double bond. And the resulting structure that we would get in this case would be a double bond up on top. We would still have the single bonded oxygens on the left there and the right. And because it does have a charge, we typically do put brackets around the Lewis structure, and we do put the charge on the outside. Now what we have done is made a structure here that, frankly, it's all good. This oxygen, 2, 4, 6, 8 electrons. This oxygen, 2, 4, 6, 8. Oxygen over here, 2, 4, 6, 8. Carbon now by double bonding, 2, 4, 6, and 8. Everybody has 8 electrons. There is still only a total of 24 electrons on that picture. And we have a nice little structure that I just highlighted green all over the place there. Now, could you have double bonded to the left or right there on those oxygens? Absolutely. And if you did, you would get similar structures. So instead of taking the electrons from here, you could have went here, and you would have ended up with a double bond to the left and single bond on top and to the side. Also bracketed it up, and also a little two-headed arrow between them. You could also double, yeah.
So I know in terms of like the Lewis structure that can work, but like for example, like that wouldn't be besides carbonate. Like if we had a double bond on a different oxygen.
It wouldn't. It is carbonate, yeah. So it's still it's the same structure. It's just kind of turned, if you will. We'll talk about what's happening in just a second in terms of those electrons, and maybe that'll answer your question a little bit better. But we could double bond here to the right, and we would end up with obviously a single bond here on the top, a single bond here on the left, and we would have a double bond over here with not that many electrons would be bad. I know I failed chemistry. It's okay. Get rid of that there. There we go. But I kept trying, and that's the important thing. All right, there we go. All right, so we're going to bracket this guy up and put a -2 charge there. And now we have three structures that are what are referred to as being equivalent to each other. These are what are referred to in the business here as resonance structures. And resonance structures occur when we have this exact situation. We have these double bond electrons, which are what are referred to as being delocalized. And because we could at some point be at the oxygen on the top, they could also be at the oxygen to the left or to the right. So for example, when we talk about those electrons that we brought in, for example, to make the bond, at any given point in time, it may be up here at top, but then it can move over to the guy on the right, which is why it's referred to as being delocalized. It's not staying in one place, which is referred to as being localized. So delocalized means it's moving. So those electrons also could be this way. And to answer your question, they're all three still considered carbonate because the true picture is some version of all three of those together. Yeah, is some hybrid of all three of those together. So these are just a representation of carbonate because those electrons can move. So at any given point in time, it could be at any of those locations. And the true structure, if you could figure out what the true structure is probably somewhere between the mixture of all three of those together. And basically, this is sort of what's sometimes referred to as the resonance hybrid. It shows basically, at any given point, those electrons could be moving. So they're not just kind of hanging out at one place all the time. They're just kind of moving around and stuff like that. So that's why when we move the double bond around, we're not necessarily making something different, which I think was your question, right? If I move it to the left or the right, is it no longer carbonate? It's still technically carbonate, but it's just these structures here are not necessarily telling the entire perfect story of it. It's somewhere in between these three structures is where the true structure of carbonate lies. So, yeah. All right. So whenever you have an opportunity like this, you can draw three equivalent structures. If you are asked to draw all the resonance structures, you should draw all three of these, obviously, that are in the boxes there, or the brackets. If you're asked just to draw the Lewis structure of carbonate, any one of the three is perfectly acceptable. Again, if it doesn't ask you to draw all the resonance structures or anything like that. Any questions on that? And again, these are delocalized electrons, which, as I mentioned, are moving around. Localized electrons are kind of ones that aren't going anywhere. They're just going to hang with that atom the entire time. They're not going to move to any other location. All right, let's try a few more here just to make sure. Why don't you draw some nice Lewis structures maybe for each of these? Why don't you do, let's do SH2, CO2, a little HCN. Why don't you draw CH2O, NH4 plus, and why not? I'll squeeze it in there. ClO3 minus. All right, let's take some time, draw up some proper structures here. Then we'll go through it.